This presentation is one of a series dealing with cargo operations on board an oil tanker. Here we continue to deal with the basics of pumping cargo, begun in Pumping Cargo Part 1. The vessel is discharging her cargo of crude oil, and the levels in the tanks are now getting low. Throughout the discharge, we have been observing the maximum pressure allowed at the manifold of 10.5 kilograms per square centimetre. As in Pumping Cargo Part 1, we will not discuss crude oil washing, just the handling of the pumps. All three pumps are running at approximately 1,125 revolutions, giving us the stipulated maximum pressure at the manifold. Your job is to maintain the maximum pressure at the manifold as long as possible. During the discharge, the pump room should be inspected at least once every hour. Make sure no personnel enters the pump room without the knowledge of the responsible officer. Always be on your guard against accidental overboard discharge, for example through sea chest valves. We are pumping oil with specific gravity of approximately 0.9. Divide the difference between the readings of pressure and suction sides by 0.9 and multiply by 10. The head is 122 meters. Checking the HQ curve. A head of 122 meters and 1,125 revolutions gives approximately 3,100 cubic meters an hour. The high back pressure prevents you from reaching full capacity of 4,000 cubic meters an hour. Monitor the discharge continuously. The installation may shift to other tanks without notice, resulting in a different back pressure and a change of head. All pumps should run as long as possible at highest possible speed and with discharge valves fully open. Make sure pumps do not run over nominal capacity. As the levels in the tanks get lower, pressures will change and the capacity of the pumps will gradually be reduced. The pressure of the pumps will differ. This will sometimes create problems in running them parallel to the same line, as one pump may not give any flow. Consult the HQ curve to adjust speed and the pressures for optimum total capacity of pumps running in parallel. Note that these capacity curves are quite flat. These pumps are rugged. While running in parallel, they're not particularly sensitive to different pressures. Let's look at some of the factors which become important as the discharge nears completion. When you're pumping, some things work with you and some things work against you, symbolized here by a plus or minus column balancing on the suction side of the pump. All measurements are in meter liquid columns. This crude has a specific gravity of 0.9. Calculate every weight or pressure into liquid columns using this specific gravity. Remember, at normal atmospheric pressures, the manometers read 0. As we're talking here about absolute pressures, the pressure of the atmosphere must be taken into account. So, when measuring absolute pressures, we start from a vacuum, which is 0. The pressure of the atmosphere is about 1 kilogram per square centimetre. First, let's take a look at the plus column. There is, of course, the column of oil standing above the pump, and there is another 11-metre liquid column due to the pressure of the atmosphere. The inert gas pressure adds another 1.8 metres, but let's forget this for a moment. This is the minus column. Let's see what's working against you. There are losses from friction. When you pump liquid through pipes and valves, the turbulence of the liquid causes friction and loss of pressure. The pressure drop is measured in kilograms per square centimetre and converted to a metre liquid column. Net positive suction head required, or NPSH required, is the lowest head that must be maintained at the inlet of a centrifugal pump. This is the head required to avoid cavitation. Below this head, at the impeller's inlet, the eye, the pressure can drop low enough for the liquid to vaporize. If this happens, the gas formed will prevent liquid from passing. Small bubbles grow, and when they meet the higher pressure in the periphery of the pump, they collapse. This is cavitation and must be avoided, as the capacity of the pump will be reduced and it can easily be permanently damaged. You can easily hear when a pump cavitates. It sounds like you're pumping gravel. Net positive suction head required is dependent on the velocity of the liquid and the speed of the pump. The last minus is the vapour pressure. If you lower the pressure below atmospheric pressure, any liquid will boil or transform into gas. The absolute pressure at which this occurs is the vapour pressure. Here is a container filled with normal crude. At normal pressure, gas is trapped inside the volume of oil in the form of liquid. If we lower the pressure below atmospheric pressure, the lighter fractions of the crude begin to gas off. When the manometer shows minus 0.4, our sample of crude will gas off completely. Vapour pressure is therefore 0.6. Convert the vapour pressure into a liquid column. You should avoid operating pumps at such a low pressure, where oil gases off. If you don't, they will cavitate, lose capacity, and be permanently damaged. Note that the suction lines are not flush with the tank floor. Pumps and the discharge lines in our vessel are mounted more than 2 meters above the bottoms of the tanks. At the end of the discharge, a lift of approximately 2 meters must be taken into account and added to the minus column. This is what happens if the pumps are left unattended at full speed, with the discharge valves fully open as the tanks are discharged. The plus column is reduced as the level of oil is sinking in the tank. The column from the air pressure is of course the same. The difference between the positive and the negative columns is reduced. When the heights of the two columns are the same, the pump will give you problems and soon lose suction. You will have some problems pumping the volume of cargo left in the tank to shore. In our example, the two columns just happen to be equal at the level of the discharge line. This is pure coincidence and has nothing to do with the lift mentioned earlier. Obviously, the trick is to reduce the size of the negative column. You can't do much about the vapour pressure. Most of the time you don't even know its value, but you should be aware of the problem. Let's concentrate on the parts we can manipulate. Friction is lowered when the flow of liquid is reduced. Net positive suction head required is also related to the flow and the speed of the pump. A lower speed results in a lower NPSH required. So, to reduce the size of the minus column, it looks like a good idea to slow down the pump. With lower levels in the tanks, the suction sides of the pumps need your attention. Keep an eye on the suction side manometers. Pressures will drop with the levels in the tanks. Remember, when the pressure at the suction side is below zero, you must add the readings of the suction and pressure sides to find the head. With most crudes, it's a good rule to slow down the pump when the pressure at the suction side is down to minus 0.3 kilograms per square centimetre. Gradually slow down the speed of the pump in such a way that the pressure is kept at this figure for as long as possible. When the pumps reach their lowest operating speed, in this case 800 revolutions per minute, you must reduce the flow by throttling the discharge valves. In the end, it is the air pressure doing the job for you. By throttling the pump, you can also overcome the lift. You still have another positive factor left helping you, the inert gas pressure. In the end, there will not be enough oil to feed the pumps continuously. When a pump loses suction, close the discharge valve. The pressure will rise again, so open the discharge valve. The pressure will fall again, and you have to repeat the same procedure over and over again until the tank is empty. By skillfully maneuvering the speed of the pumps and the discharge valves, you will be able to manually prime out almost all cargo from the tanks. It helps a lot if the vessel has a good stern trim. The pumps are lowered and the oil will flow easier across the tank floor to the suction bells. In practice, it's difficult to manually prime out more than one pump at a time. That's why most tankers have automatic priming systems. In this system, vacuum pumps create the underpressure the cargo pumps cannot build up. When the system is started, the level of liquid in the drop separators is sensed. When the level is too low, a pressure transmitter signals the discharge valve to close and the vacuum valve to open. Liquid is drawn up in the separators and the pump is fed with liquid. So the pressure starts to build up at the discharge valve. When the separator is filled, a signal is sent to the vacuum valve to close and the discharge valve to open. The pump starts to work in a priming cycle. The pump fills and empties regularly. Watch the priming cycle. The tank is empty when the pressure at the pressure side of the pump remains at zero and the discharge valve doesn't open anymore. Close the valve to the tank and stop the pump. The tank is now almost empty, but still not dry enough. There is still some oil slowly making its way to the aft part of the tank. You're now going to strip the last remaining cargo out of the tanks using the eductor. To be able to use the eductor, you must have a sufficient volume of cargo left in the slop tanks. These are kept as the last tanks to be discharged. While you're priming or stripping the tanks, you should draw the cargo the shortest and simplest way possible to reduce the possibility of gas leaking from empty tanks. Close all the main valves separating the different lines. Here, the closed master valves are marked with crossed circles. To prime the center tanks, use the main suctions in the center line of the tanks. When you strip the tanks, use the lower suctions. A slight list can be an advantage, as the lower suctions are not in the center line. Check their positions. Stripping the cargo tanks dry with the eductor can take between 1 to 3 hours. This is an eductor. When the driving liquid passes the nozzle, inside the venturi, an underpressure builds up. An eductor will suck as long as the driving liquid is supplied at sufficient pressure. Here, cargo pump number 3 provides driving liquid to the eductor from the starboard slop tank. You are stripping cargo tank 1 with the eductor. The level of oil in the port slop tank will rise, but when the ullage is less than 10 metres, the cargo is recirculated back to the starboard slop tank through the U-pipe by gravity. As long as an eductor draws any liquid, the manometer at the suction side will show a slight underpressure. When there is no more liquid, the pressure will stay at 0. Remember, close the valve before shifting the stripping to another tank or when stopping the eductor. If you don't close the valve first, cargo may flow backwards into the tank. When all cargo tanks are empty and well stripped, you can pump the slop tanks to shore with cargo pump number 2. While you discharge the slop tanks with cargo pump number 2, drain the other lines using the stripping pump, pumping it ashore through the so-called Marpole line. On deck, the drop lines should be opened down to the main discharge. First, drain the risers above the non-return valves. Then strip the main cargo lines not in use. To be able to empty the lines completely, remember to let inert gas into the lines to avoid vacuum. Next, strip the cargo pumps. The last operation will be to strip the slop tanks with the stripping pump. Strip cargo pump number 2 and its lines the same way you did with the others. All cargo is discharged, and the cargo tanks are being inspected. Should there be a discussion claiming that the vessel is not properly discharged and well drained, you should offer to start the pumps to prove the opposite. It is a safe routine not to allow disconnection of the loading arms until the tanks are inspected and found to be empty and well drained. Let's conclude this program by showing an operation you may be required to perform, that is, taking on ballast using the cargo pumps. As our vessel has segregated tanks, the ballast system is separate from the cargo system, so using the cargo pumps would only arise in an emergency. But in a ship with no segregated ballast, you always have to be able to take in ballast with the cargo pumps. This operation is risky. Cargo leaks causing pollution can occur. There is a risk of pollution, and so you have to be extremely careful to prevent oil from leaking to the sea when ballast and cargo systems are connected to each other. To prevent oil spills, you must use a special start-up technique. You must create and secure at all times a lower pressure in your vessel's piping system compared to the pressure at the sea chest. So water flows to the pump as soon as the last sea valve is opened. There are 2 sea valves, both manually operated gate valves. These 2 valves have been pressure tested before arrival as a part of the normal routine. You know they are tight. Here you're going to ballast cargo tank number 4 with cargo pump number 1. When you start the pump, you have to be a bit brutal. As you know, we don't normally start a pump with valves closed at the suction side. But this is what you have to do when ballasting with a cargo pump, to be sure you get a low enough pressure in the suction line. You may even crack open the discharge valve just a little bit to ensure immediate flow through the pump. The man operating the sea valves is instructed to open only the inner one. He should then be standing by to open the last valve at a given and agreed signal when the pump is running okay. He's also instructed not to fully open the valve at once. If the pump should trip, he must close the valve as fast as possible. The man in the pump room is standing by, and you're now starting cargo pump number 1. Everything seems to be normal, and you're speeding up the pump. The pressure at the discharge side rises, and the pressure at the suction side drops below zero as expected. Reaching 800 revolutions, the manometer at the suction side shows minus 0.3 kilograms per square centimetre, and you decide to open the C-valve. As soon as the C-valve is opened, the pressure at the pump changes immediately when the water flows through the pump. You're now adjusting the speed and regulating the back pressure and the head by manoeuvring the discharge valve. In our vessel, the speed of the pumps will be approximately 1,000 revolutions while ballasting. There is no point running a pump at full speed if you can reach a high capacity running the pump slower. Remember, this way you will save fuel and money. In this case, you're adjusting the speed and the pressures to get a head of 86 meters. Discharge side shows 9.3 kilograms per square centimetre, and the suction side 0.4 kilograms per square centimetre. You are pumping seawater with a specific gravity of 1.025. From the HQ curves, you can see you are pumping approximately 3,700 cubic meters an hour. Be careful to obtain a suitable head while pumping ballast. Possibly more pumps have been damaged during ballasting than during discharge. This is because it is so easy to run the pump in overcapacity with too small a back pressure and head, with the discharge valve wide open. If you know the principles and run the pumps of your vessel with skill and care, you will save a lot of money discharging and ballasting, and you will, of course, save yourself a lot of trouble. May we wish you good pumping. The topics raised here will require some thought and discussion to ensure full understanding of the principles and how they relate to your vessel. Rerun this tape and cargo pumping number 1, if necessary, and discuss with others on board.